Okay, welcome back. This is section now 10.6, I believe, and um, this has stuff with shortest path algorithms in it, but we're going to kind of skip that. You could read it in the book if you're interested in that kind of thing. We'll focus in on the spanning trees because that's where the WebAssign homework is. So what is a spanning tree? A spanning tree is a subgraph that is a tree. So you're given a graph G. If you can find a subgraph, which is a tree, that is a spanning tree. Okay, so it's a subgraph that is a tree. Okay, okay. So example, I think this was problem 2 in the book. So we have a graph, and it looks like that. Okay, so let's get some spanning trees. There's more than one in this case. Okay, so a tree has to have how many edges? Well, if there's 4 vertices, there'll be 3 edges, and there can't be any circuits. Okay, so one example of a spanning tree would be this guy right here. Okay, 3 edges, no circuits. Another example would be this guy. There's probably like 7 versions you could imagine if you want to go through all of them. It could be a fun exercise. Okay, this one. Okay, looks like a Z. Okay, in this section, they're going to be putting in weights on them. So 1, 2, 3, 4, 5. Okay, and then they look at the different spanning trees. So this spanning tree has weight 1, 5, 4. In other words, its total weight is 10. Okay, this spanning tree here, the next one, 1, 4, 3. So its total weight is 8. And then the Z tree here, Z 2, 5, 4, is 11. Okay. So if we were looking for the spanning tree with least weight, it would be the middle guy. Okay. So one thing you may notice is, like, gee whiz, that I don't know a good way of finding all the spanning trees. Okay, so that's one problem. And then even if I could identify all the spanning trees, I don't feel like going through and adding up all of the different, doing a brute force and setting that. Maybe I could program a computer to do it, but I wouldn't personally want to do it. Is there a quicker way? And yes, there is. And these are the minimum spanning tree algorithms. There are 2 of them. Okay, and usually the way I handle these algorithms is I kind of read them and get the flavor, and then I go through and do some practice exercises and kind of feel how they work, and then I just kind of do it without the algorithm. So the algorithms are sometimes a little complicated to follow, right? So anyways, the Kruskal algorithm is the first one. I'll write it out in all of its glory for you. So our input will be some sort of weighted connected graph. So G is a weighted connected graph. Okay. And here's the algorithm. So what are we trying to do? We're trying to build this subgraph T, and one other thing, M is going to stand for the number of edges in T, and that will be our counter. Because once M gets to n minus 1, supposing that, maybe we should also say G has n vertices. Okay. So as soon as M, we'll start with M equaling 0. As soon as M gets to n minus 1, then we know we're done, right? Because it will be a tree. So let me make that more clear. So first off, T is a set of vertices. You start with T, all of the vertices of G. So T is a set of vertices of G. Okay. And then E is a set of edges of G. And we, again, what we're doing is starting with M equaling 0. Okay, so those are the number of edges on this new graph T. And then we kind of have a while loop. So while our m is less than this n minus 1, which will be the number of edges on the tree, first you pick an edge of least weight, pick edge E of least weight, and then 3b, delete this edge from the edge set E, big E, and then 3c, you kind of look and see if adding that edge to T will cause a circuit or not. So if it doesn't cause a circuit, you can add it in, but if it does, then you just throw it out. Okay, so if adding little e to T does not produce a circuit, then add e to the edge set of T and increment m. So, and then let m be m plus 1, right? Okay, and then once you hit n minus 1, you know you have a tree, and you can end your while statement. And then your output should be that tree. Output is T, which should be a tree. Right, so let's try one. And I'll find an example in the book. And this is the annoying part, having to draw this thing out. So this is problem 5 in the book. Okay. A, B, C, D, E, F, G. Whoops, this is E. And then this is F, and this is G. So A to B has weight 1. B to C is a 7. C to D is a 4. D to F is a 5. F to G is a 6. And then G to B is an 8. And then A to E is a 9. And then E to F is a 2. And then E to D is a 3. And then G to C is a 10. Okie dokie. So to initialize this thing, kind of what we do is just redraw all the vertices, and we can record where we are with M, and we're also going to record the edges as sets as we go along. Okay, so M is originally set to be 0. Okay, I don't know why I drew it like this, but okay. And then we want to go up to 1, 2, 3. How many vertices are there? 1, 2, 3, 4, 5, 6, 7 vertices. So we need to go to 5, and then 6. We need 6 edges. And in the slots, I'll put what the edges are. So in WebAssign, you're going to have to put them in as ordered pairs in these curly brackets with commas in between them. So your answer, will be everything except those bars that are there from my table. Okay, so I would come over here and first just draw a bunch of little dots, and I think we're calling that T, right? So T is a set of all vertices of G. Yeah. Okay, so what do we do? E is a set of edges of G. So M is currently at 0. So it's definitely less than n minus 1. N minus 1 is 6 because we have 7 vertices. So pick an edge of least weight. So the edge of least weight on this graph is 1. Let me label these A, B, C, D. Oh, I missed one. Careful. E, F, G. So pick this guy and then decide if you can add that to this graph of vertices, which is T. Okay. So I pick this edge E, and I'm sort of deleting it from this graph on the left by putting a little slash through it. And then I determine whether or not that edge causes a circuit. Okay, it doesn't cause a circuit on the graph on the right. There's nothing there, so there's no way. So I can add that to the graph. Okay, so my first edge is AB. So down on my chart, I put AB in the curly brackets. Okay, okay. So now M is equal to 1. I go over to then the graph again and look around for the least edge that is EF. So you delete it. Can you add it to T? And in this case, yes. Okay, so I'm going to add that in. And so EF is the next in my chart. Okay, so M gets incremented to 2. Okay. Then I look for the next edge. So 3 is right here. Can I add it to the graph without causing a circuit? Yes, I can. So I add it. Over here it's 3. So I have ED now added in, and M is 3. Next edge of least weight is 5. No, it's 4. Sorry. So that's CD. Can you add it? Yes, you can. So add that in. So CD. M goes to 4. So now we're at 5. I look around for my next one, and that's FD. So I delete that. Can I add it? No, you can't, right? So if you tried to add it here, it would be bad news because then CDF is going to be a circuit. Okay, so you can't add that guy. But so what you do is just delete it from the original set of edges and move on. Okay, so the next least weighted edge is GF. Okay, so delete that and then see if you can add it. And yeah, we can add that one because it doesn't do a circuit. Okay, so you add that to the set. Then look around. We're at M equals 5, so we're still working in the algorithm. Look around. 6 and then 7 is the next least weight. That is right here. Can I add it to the graph? And yes, you can. So BC. M is now at 6, which is going to push us out of the while loop. So N while, and the output is T. Okay, so this is our spanning tree of least weight. And this was 7. Okay. Okay, so in WebAssign, the answer they want is this right here. Okay, with the commas in between. It's a little weird to write, and they don't exactly tell you how to do it in WebAssign. It's a little confusing. So in WebAssign, you would put this, etc. I don't know if that's a C or a D. I don't remember. So just all the way up to BC. But you have to write out each one. Okay, my C's look like E's. I apologize. Okay, all right, so that's the first algorithm. The second algorithm is a prim algorithm. So B prim, and in all of its glory, let me write out the algorithm. So we have an input of G again. So it's the same, you have the same goal in mind. You want a minimum spanning tree. Okay, so the input is G, which is a connected weighted graph with n vertices. And then the algorithm here, which will build us this T, which again is this minimum spanning tree. So how does this work? So first you pick a vertex, okay? We'll call it cursive V of G. Let big T be a graph with just vertex V. Okay. Secondly, then, we'll say this big V be the set of all vertices of G, big G, except this one we just picked, little cursive V. And then we start our for loop. So for I going from 1 to n minus 1. So again, we're building a tree. So I is representing the number of edges we have. What we do is find an edge G, find edge E of G such that, first off, E connects big T to big V, and two, secondly, E is of least weight. Of all these kind of bridges. I'll just call them connectors. Then you're going to kind of add that one in. Okay, so you'll let W be the endpoint on the other end of E. So that endpoint that's in the other graph V, and then so this should be step 3A, and then step 3B, add E and this W to T. So maybe that's like a cursive W. Add E and W to T, and delete W from V. Okay, and then you increment your I and repeat until you get the full graph, and then the output should be your spanning tree. Okay. Okay, this is easier done than said. So there's a lot of T's and V's and then capital V, and then, it's just, oh my gosh, it's a nightmare. So let me find an example and we'll try it. So let's try number 9. And we have 1, 2, 3, 4, 5, 6, 7 vertices. So there's a loop all the way around, and then the guy in the middle connects to all of the vertices, like this. And then I'll get some weights on there and some labels for the vertices. So I'm going A, B, C, D, F, and G, and E, and weights 4, 3, 7, 7, 10, 11, 12, 4, 4, 3, 5, and finally, I believe 1. Okay. So you'll pick a vertex. I'll pick vertex A, okay, and I'm going to have to redraw the graph in order to pull this off. Okay, it's not a lot of fun. Okay. So throughout the algorithm, they're talking about two graphs basically. I mean three graphs really, but the main ones they're working with are T and V. Okay, so T is kind of the thing you're building, and we'll start with A. Okay, so I'll say that's T, and then V is the thing you're kind of connecting to. Okay, so this blue thing would be the V part. Okay, and the algorithm says basically just look at all the connectors between T and V. So right now the connectors are AG, AE, and AB, 4, 3, 3, and then pick the one with the lowest weight that connects T to V. Okay, and that's all they're saying. Right, so find an edge E of G such that 1, E connects T to V, and 2, E has least weight. So again, here's T, the red, here's V in the blue. I look at all the ones that connect T to V. Okay, so that's AG, AE, and AB, and I could pick the one with the least weight. If there's two of them, well, hey, just pick one or the other. It doesn't really matter. Okay, okay, so 1, 2, 3, 4, 5, 6, and then we have this. Whoops, I want to do those in white. Okay. Okay, so this is A, B, C, D, E, F, G, and I'm picking this as my first edge. Okay, so in that case, I don't know. We can redraw it if you wish. I kind of just, okay. I guess it's not that hard to draw. Right, so now the new T graph is this. This is our new T, and the new V is everything else. Okay. And again, okay, and I need to record somewhere my answer. So the first edge is A to B. Okay, okay, so again, we have T, we have this graph T, and we have this graph V. We want to look at the connector edges and find the one with the least weight. Okay, so the connector edges BC, AB, and then AG, and between those, which one is the least, right? So BC is 7. Oops, I missed an edge. BE is 4, AE is 3, and AG is 4. So AE would be our next edge. Okay. And you see T is going to get bigger and V is going to get smaller, right? So our next graph, how the heck did I draw the 3? And there's one in the middle. Okay, so now what do we have for T graph? So I have A, B, and E. It's this junk. And then the rest is blue. And after a while, you won't have to go through this process. You know, you could just kind of get an intuition for how the program is working, right? So now we're looking at these bottom spokes, so to speak, of that graph, and I'm looking for the least weight. So there's a 4, a 5, a 4, 11, a 7, and a 7. So you probably want to go with one of the 4s. And I think I missed a vertex or something when I redrew it. See, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6, 7. 1, 2, 3, 4, 5, 6, 7. No, I think I got them all. Sorry. Okay, so which one do I want to add in? So I want to add in AG. That's a 4. AG or EF. It's kind of, I should have labeled the stupid things. I think I'll go with AG. So sometimes there's more than one answer. Okay. And kind of let me continue on. So I'll just sort of draw over. It's going to get real ugly, but I'll sort of draw over. So where are we now? I added in AG, right? So I have T being A, B, G, E, and then V is these three. Okay. So I'm looking at these connectors, 7, 7, 7, 11, 4, and there's a 1 there as well. So I'm going to add in the 1. So GF would be my next. Okay. So my new sets, T would be this chunk. And then V would just be these two last vertices. Okay, so I have these 4 edges that are connecting. So 7, 7, 11, and 12. So I'll pick BC to be my next guy. Okay, and then my graph is looking like a mess. So let me scroll down to the bottom graph. Well, no, let me just put it on the original one. So where am I right now? Let me circle them in yellow. On the left, I'm going to use the graph on the left. So I have everything plus C circled. And the last guy I need to circle will be D. So you have 10, 11, and 12 connecting. 10 is the smallest one, so you're going to go CD for your final edge. Okay, so it's a nightmare, but if you could find a nice way to kind of do that and explain it to people, I mean, that would be where the money is. But hopefully that isn't too obnoxious with all the circles and stuff. Okay, but it's like, if you don't get it, then go back to the original algorithm and kind of read through it. What I do is just rewrite the algorithm in my own words, and then I try it. And there's extra exercises in the book, so I know the homework is ridiculous. There's just like 2 problems there. It's kind of a waste, but there's that. Okay. So I think it's in your best interest to try some of the ones in the book. I'm tempted to give some take-home homework that you can do with regards to this, so I may actually do that. Anyways, thanks for watching, and we'll see you next time.